How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some ideal gas equation practice problems. So we're going to be kind of focusing on this whole PV equals nRT, where pressure times volume has to equal the number of moles times the gas constant times the temperature in Kelvin. Let's take a look. Number one, a 1 mole of gas at STP, standard temperature and pressure, will occupy how many liters? This is known as the molar volume. This might be a number that you've since memorized. It's 22.4 liters, but let's work through how to get it. So we got PV equals nRT, and we're trying to solve for volume. So you got to divide each side by pressure, cancels out pressure over there. Now it says at standard temperature and pressure. So it says, hey, for 1 mole at standard temperature and pressure, so I'm going to use atmospheres. So my R is going to be that 0.08206 liters times atmospheres per mole Kelvin, times by the temperature in Kelvin. Standard temperature is 273 Kelvin, divided by the pressure of 1 atmosphere. And when you do that, atmospheres cancels out, moles cancels out, Kelvin cancels out, and you're left with 22.4 liters when you round it to 3 sig figs. So that is known as the molar volume. 1 mole of any gas at STP will occupy 22.4 liters of volume. All right, number 2, how many moles of gas are there in a 45.0 liter container at 25 degrees Celsius and 500 millimeters of mercury pressure? So again, we're going to start with PV equals nRT, and the question is, well, what are we solving for? How many moles? So we got to get N by itself, divide each side by RT, cancels that on this side, and now I got my moles. So now I can just kind of plug and chug. My pressure, I got 500.0 millimeters of mercury times my volume of 45.0 liters divided by the R. If I'm using millimeters of mercury, it needs to be that, 62.36 millimeters of mercury times liters over mole Kelvin. Sorry, brain fart. And then times by the temperature in Kelvin. Well, if it's 25 C, it's 298 Kelvin. Remember, you add 273 to your Celsius to get your Kelvin. And now I can just pick up my calculator and plug and chug, and I get 1.21 moles. That's my final answer. Cool. Number 3, a little more complicated. How many liters of carbon dioxide would be produced by reacting 7.7 kilograms of sodium bicarbonate with excess hydrochloric acid at 25 degrees Celsius and 1.5 atmospheres? So here we have the balanced chemical equation. And it's saying that we have 7.75 kilograms of sodium bicarbonate. So we got 7.75 kilograms of this stuff, and it's asking, how many liters of CO2 would we make? So we're going to have to do this problem in steps. First step is going to have to be to convert those kilograms to moles. Right? We got to go kilograms, grams, then grams of moles using the GFM. Once we have moles of that, then we can go, hey, what is my mole to mole ratio for the sodium bicarbonate to CO2? And then once I got that, 3, now I can use my PV equals nRT to solve for my volume. Let's start. I got 7.75 kilograms, which I times by, hey, for every 1 kilogram, that's 1,000 grams. And I end up with 7,750 grams of sodium bicarbonate. Now, if I do the math for the GFM, well, I got sodium. There's 1 of them, and each of them is 22.99 grams per mole. What else we got? Hydrogen, there's 1 of those at 1.01 grams per mole. Carbon, there's 1 of those at 12.01 grams per mole. And those oxygen, well, there's 3 of them at 16.00 grams per mole. So when I add all that together, I get a gram formula mass for sodium bicarbonate as 84.01. Is that right? Yeah, 0.01 grams per mole. So now that I got my grams and my grams per mole, I can do a little math. I go, all right, well, I know that for every 84.01 grams, there is 1 mole. When I do that math, I got 92.25 moles of NaHCO3. Now, since it's a 1-to-1 ratio to carbon dioxide, it's also the moles of CO2. Now, I want to know, well, what volume would that be? Well, I got my PV equals nRT, and I'm trying to solve for volume, so divide each side by pressure. And I got my equation, so now I could plug it all in. My moles, I got 92.25 moles times my R. Well, if I'm using atmospheres, it's 0.08206 liter atmospheres per mole Kelvin, times by the temperature in Kelvin. Again, 25C would be 298 Kelvin. And then divide by my pressure of 1.5 atmospheres. And when I do that, I get to 2 sig figs, 1,500 liters as my final answer. And number 4, I'm going to turn the page for this one. Number 4, 6.022 grams of CH4 gas is added to a 30-liter rigid vessel at 402 Kelvin. What is the pressure of the gas in atmospheres? So again, start with my PV equals nRT. And I gotta get pressure. So I just divide each side by volume. Volume cancels out. Boom. Pressure equals nRT on V. So now I can just plug and chug. Oh, wait a minute. I need to know how many moles that is. So I get 6.022 grams. Well, what's the gram flowing mass of CH4? I think it's like 16.05 grams for every 1 mole. Grams cancel out, and I end up with 0.375 moles of CH4. So now I can plug that in. I got 0.375 moles times, well, okay, they want the pressure and gas in atmospheres, so my R is going to be that 0.08206 liter atmospheres per mole Kelvin, times by my temperature in Kelvin, 402 from the problem, divided by my volume, which is 30.0. Now when I pick up my calculator, beep bop, boop, I get 0.413 atmospheres as my final answer. Bada bing. All right. Number 5, what is the volume in cubic meters of a 0.25 mole sample of gas at 72.7 kilopascals and 15 degrees Celsius? So let's start with an issue. So we know that we got liters, they want it in cubic meters. I know that 1 milliliter is 1 cubic centimeter. So let's think about it. If I had 1 cubic meter, that'd be 1 meter by 1 meter by 1 meter. It's the same thing as saying 100 centimeters by 100 centimeters by 100 centimeters. So when I do that math, and I do 100 centimeters cubed, I end up with, was it like a million, I think? That sounds right. 1 million cubic centimeters, or 1 million milliliters, is equal to 1 cubic meter. So if I converted this to liters, 1 cubic meter is equal to 1,000 liters. And I'm going to need that conversion factor eventually. So I got my PV equals nRT. They want the volume, so I divide each side by pressure. Now I got my volume right there. So now let me plug and chug. I got 0.25 moles times my R. If I'm using kPa, I need to use 8.314 kilopascal times liters over mole Kelvin, times by 15 Celsius would be 288 Kelvin, divided by the pressure of 72.7 kilopascals. And when I plug and chug and get that, I end up with 8.23 liters. So now I gotta convert that. I go, hey, if I need cubic meters, I know 1 cubic meter is 1,000 liters. So when I multiply that, I end up with 0.00823 cubic meters as my final volume. All right, number 6, how much HCl gas is needed to react with excess calcium to produce 11.4 liters of hydrogen gas at 1.62 atmospheres and 62 Celsius? So let's start by figuring out what the balanced chemical equation is. Saying I'm reacting HCl gas with excess calcium to produce hydrogen gas. And then, well, what's left? Well, I'm going to be left with the chlorine and the calcium. What compound are they going to make? Calcium chloride, CaCl2. So in order to balance this, I have to put a 2 in front of that HCl. So now I got 2 hydrogens on both sides, 2 chlorides on both sides, and 1 calcium on both sides. Awesome. So you could do like a bunch of elaborate math with PV equals nRT, but since these are both gases and we're talking about the same set of conditions, then the amount of moles is going to be proportionate to the volume for each of those. So basically, if I had 1 liter of H2 gas, I would need 2 liters of HCl to make that. So it's just kind of a proportion. I take a look, HCl to H2 ratio is a 2 to 1. So if I'm trying to make 11.4 liters of H2, how much HCl do I need? It's going to be twice that. So cross multiply and divide, I get 22.8 liters. That is going to be the easy way to do it. All right. I hope you found it helpful. I'll see you in class. Goodbye.